Welcome to Pattern Analysis. The topic of this week is sampling, and we perform also sampling with the purpose of inferring a Gaussian mixture model with a variable number of components. Let's go. So the role of sampling in Bayesian models. Generally, sampling draws one or more observations from a distribution. So an example for this is when you use a generative language model. Here, the notion of one sample depends a bit on the context. So you can say one reply of that language model is one sample from the distribution of plausible replies. Totally makes sense. But you could also say that every individual token, so a token is like half a word or a word, part of a word, is one sample from the distribution of plausible sentences or plausible words. So this is an example for efficiently performing inference in a complex model. So one sample is one representative draw from the model's posterior distribution. And now you could say, well, let's try out the same prompt over and over again, and let's make sure that the language model doesn't memorize what you asked it. So you could reset the internal state, ask the same prompt again, ask the same prompt again, and then you get, like, what you will see is you get different replies. And the set of different replies is essentially an approximation of the posterior distribution of that language model. So the applications of sampling are actually a bit broader. They are not limited to the posteriors of generative AI systems. So very generally, you could think about sampling as moving from the latent variables to the observations. And in that sense, you could say, well, sampling is something like a reverse operation to density estimation. But there's also another perspective. So the sampling itself can be part of some iterative optimization procedure. So in that sense, then sampling is only a computational tool within a larger processing chain, you could say. So, for example, one example that we will see later in pattern analysis is that we are sampling training data with the goal of training an ensemble, so a combination of different classifiers, for example, regressors. In our random forest training, we will explore this more. Also, if you think about, for example, the training of neural networks, their training data is sampled with the purpose of making the training more efficient. So in the case of neural networks, this is part of the stochastic gradient descent algorithm for neural networks. Sampling distributions can also mitigate computational bottlenecks during inference. And sampling conditional distributions can iteratively adapt a model to the data. So this is what we will be doing for the Markov chain Monte Carlo fitting later. So, so these are the two. I think these are plenty, as you can see, these are like plenty of applications for which sampling algorithms can be used. We will look at three specific algorithms. The choice is a bit arbitrary, but all of these three are classic sampling methods. So the first example is rejection sampling. Second is a variation of that, the so-called adaptive rejection sampling. And the third choice is Markov chain Monte Carlo sampling, which we will also be using for the GMM fitting. So the sources for this lecture are the book by Bishop, section 11.3, 11 until 11.1.3, 11.2.1 and 11.3, and a paper by Rasmussen about the fitting of Gaussian mixture models. This I upload to StudOn. And we will look at it in our meeting. So here's an example for avoiding computational bottlenecks. So you can use sampling as an approximation method for analytic calculations. And one very useful example is to evaluate an expectation. Yeah? So the expectation of a function f, very simply, you evaluate the function f for every possible location z and multiply it by the relative frequency of z. So how often does this event occur and to what value does it evaluate? And this you integrate over the whole domain of z. And in many cases, there's no way of solving this analytically just because you're not able to solve that integral. So nevertheless, if you can sample from this distribution P of z, then you can draw L samples from P of z and evaluate this function f for these L samples and just calculate the average out of this. And this is actually an estimate for the true expectation. And this is can be a very good estimate actually. No? It's an unbiased estimator. So this means that the limit of that expectation actually goes towards the true expectation, and the variance of that estimator is indeed like just the expectation of that function minus the true function value squared. So the accuracy of that estimator does not depend on the dimension of z. So this means it's super useful if z is a high dimensional variable, because still with comparably few samples you can get a good estimate for that high dimensional, for the expectation of that function evaluated over this high dimensional domain. Okay, we already heard about a sampling algorithm. It was inversion sampling. We had it in the first lecture. The reason why we would like to look more into sampling algorithms is that it's not perfect. So there are quite some limitations here on our inversion sampler. Yeah? Inversion sampling can in principle operate on very general, like any distribution, doesn't make an assumption about its functional representation or so. But the practical usefulness of that inversion sampling is quite limited, because it requires a full representation of the density at every location x that we might possibly evaluate. So whatever your representation for the density is, this means that effectively you need to sample it in like equidistant, in an equidistant scheme, for example. Maybe you can do it somehow smarter, but in principle you're almost forced to convert this density representation to a histogram. And histograms, we discussed it in our first lecture, are difficult to really nicely calibrate to the data. So either these histogram bins are quite coarse, so relatively large bins covering relatively large areas, so you miss out some details, or you make these histogram bins very small, but then you need to fill them all with data, because these are B, if you divide the domain along one dimension into B bins, raised to the power of D, this is the dimensionality, you recall this from lecture 1, yeah? B raised to the power of D bins, which grows very fast. So, and each bin has to be filled with several data points for sufficient statistics, so it requires loads and loads of data. So, so either your statistic is bad because you don't have so much data, or your statistic is bad because the histogram bins are too large. So in any case, you buy into some approximation errors, and any approximation error that you have in your histogram automatically propagate to the inversion sampler. Yeah? And this is a bit of a not so nice property of the inversion sampling. So let's have a look at alternatives. Here's a very general alternative, and this is to sample from parametric standard distributions. So if we think about a Gaussian distribution, or if we think about exponential distributions of the form lambda times e raised to the power of minus lambda y, or Cauchy distributions, which is something like 1 divided by pi times 1 divided by 1 plus y squared, then for these three types of distributions, there are analytic mappings known, analytic mappings from uniform distributions to these target distributions, like the Gaussian, the exponential, the Cauchy distribution. And this makes things very simple, because usually, like, no matter what operating system you're working on, like, or in what programming environment, usually you always have some algorithm there pre-implemented that gives you a pseudo-random number drawn from a uniform distribution. So this is something that we have. So what you can do then is that you say, okay, I want to draw a sample from a uniform distribution, and then I like to use my analytic transform for that sample to the target distribution P of y, using this analytic mapping f of my random number, uniformly distributed random number. Okay, if this is a multidimensional case, just a small technical detail that I want to mention, you need to include the derivative. For 1D you need to include the derivative or the Jacobian for a higher dimensional case. For having like a proper volume transform here, no? So P of y equals P of z times dz over dy, or here the Jacobian that you calculate these like partial derivatives. Okay, but in any case, so this way of sampling and having like a uniform number, having an analytic transform, is highly efficient, and it's more or less almost identical to inversion sampling if you think about it. So instead of calculating the cumulative density function as in inversion sampling, we calculate this mapping f of c. Okay, so this is one possibility, and it's perfect for these special distributions which you might use in your modeling. If you have other distributions, then you need more more general algorithms, and here's one possibility. In rejection sampling, you have this idea that maybe it's possible to get for a specific location P of C an estimate, up to an unknown normalization factor 1 divided by ZP. So this is a normalization term. So let's say the scaling is unknown, but other than that, we can evaluate P of C. So in that case, the idea is to define a simpler distribution, QZ, and a constant K in order to form an envelope to this function with the unknown scaling. And all that we need to make sure is that K times the simpler distribution is everywhere larger or equal than this P of C that we want to sample from, at all locations C. If this is possible, and this oftentimes can be done if distributions are not terribly complicated, then it's not so hard to provide an upper bound. In that case, what you can do is you can draw a sample Z0 from Q of Z, so the simpler envelope function, and then you can draw a sample U0 from the uniform distribution between 0 and K times Q of Z0, and then reject the pair C0, U0 if this uniformly drawn sample is larger than P tilde of Z0, and otherwise return C0. So let's have a what's happening. Let's have a look at this picture, and let's just go through these steps once more. So first of all, we draw a sample Z0. So along C we have an envelope function. This is the envelope function. From that envelope we draw a location C0. This is what happens here. So here, C0. This is C0. Now we know this is an envelope, and the actual function value is smaller than that. Okay. So, and we can evaluate PZ0. So maybe it turns out this is PZ0 has this value, this magnitude. So what we do is along this whole line we draw a uniformly distributed number, and if it happens to be in this part, that is part of the actual distribution, we keep it, otherwise we reject it and start from the beginning. So why is this a valid algorithm? The reasons are given below here. So if we say we first draw Z0 according to the envelope and then draw a uniformly distributed value along that area of the envelope, what we then have is a uniformly distributed area along the envelope. Yeah? It could be any of these points here with equal probability. And if we now say we reject everything that is outside of the true distribution. So this is the true distribution, but we can only evaluate it at specific locations, not everywhere. Yeah? Then we have a uniform distribution in the area of the actual distribution. So it's a valid sampling algorithm. So the algorithm is nice, but it has a small problem. It becomes inefficient if the difference between the envelope and the actual function is too large. Yeah? You can say, okay, this is not surprising, because then I have an excessive number of rejections. So I keep drawing number, I keep rejecting. This is a problem. Now, particularly, this can be the case if we just don't know what could be a better fitting envelope Q for my data. And there it turns out, do we have some prior knowledge about the distribution? Yeah? And the idea is this: if I do have a log concave function, in that case, the so-called adaptive rejection sampling might actually be a good idea, yeah, to get a better fitting envelope. So the idea of adaptive rejection sampling is to construct this envelope ad hoc from the distribution P of C in such a way that they say, well, let's have a look at the log of P of C. Because if it's a log concave function, then it looks somehow like this. So if we look at the log of P of Z, then the log concave function has a curvature like this, and the envelope is approximated as a piecewise linear function in log domain. Yeah? It's a little hack. Linear functions always very cheap. No? And fitting a set of lines to the log of the function is equivalent to fitting a piecewise exponential distribution to the original function. Yeah? So that means the envelope, not in log domain, so in the actual data domain, has a form of k times lambda times exponential. So this is an exponential function. So for distributions that are somehow related to the exponential family, the adaptive rejection sampling gives a very nice, very tight envelope. Yeah? Okay. Okay, so the problem, like where rejection sampling, also adaptive rejection sampling and so on fails, is if the number of variables becomes large, or attributes within one variable, same problem. Yeah? So consider a case where a random variable x has many attributes, or a model consists of many somehow dependent random variables x1 to xn. Yeah, same problem. So, for example, the second case happens when we model a sampling-based solution for our Gaussian mixture model fitting. There, what variables do we have? The number of components, the component weights, pi 1 to pi k, the mean of each component, the covariances of each component. This is the problem. And some hyperpriors for all the random variables. So in that case, so if we have such a large number of variables, one sample would then be a full set of assignments to all these unknowns. And if we would use rejection sampling or adaptive rejection sampling, then we would be running into the problem that the gap between Q and P tilde increases, because in higher dimensional spaces, more and more data is on the margins, and we will talk about this more when we talk about dimensionality reduction. So, but more practical. So, let's say we would have envelopes around all variables of the Gaussian mixture model. If we would then draw a set of these variables, then one of them will probably always be outside of P tilde. And the more variables we have, the more likely it will be that one of the sampled variables will be outside of the space. And then we would have to reject the whole set of parameters, which can be very tiring. It can run for a very long time. So instead, what one can do is one can pursue a strategy that is called Markov chain Monte Carlo sampling. And there you essentially draw from the conditional distribution like one variable at a time and iterate this. And that way you are enabled to sample from very complex distributions, as long as you can define these conditional distributions, of course, from which you actually sample. Okay, so just to rephrase this in other words, the idea is to sample from one variable at a time and iterate this and reuse the recently sampled values. So you can think about this as an optimization procedure where you're updating one variable at a time, and you repeat until it converges to some value. Okay. More abstractly, let's call the iterations tau. Sample an iteration tau from a state space of variables C of tau using the previous iteration variable, the variables from the previous iteration C1 to C tau minus 1. And now the Markov property comes in. It's defined as a Markov chain. Markov chain means that it only remembers, or it only considers first order statistical dependencies. So this means the conditional distribution of C tau plus 1 given all previous time steps, C1 to C tau, is just the same as the conditional distribution for Z tau plus 1 if it only remembers the previous time step. So in other words, we know where we were yesterday, but we have forgotten about all the past. This doesn't mean that the past doesn't matter. Because there must be a reason that we were at that location where we were yesterday. So somehow we got to that location yesterday, but for calculating today's location, we don't take the past into consideration, so only our previous position. Yeah. Okay. So there are different Markov chain Monte Carlo algorithms. If you want to discuss this with your favorite AI, you will probably come past the Metropolis Hastings method. It's super well known. What is also well known is Gibbs sampling, and this is the particular method that I want to discuss here. So this is the one with the conditional distribution, sorry. Yeah, so Gibbs sampling. Given models for conditional distributions for M variables, the goal is to approximate the distribution P of C being a joint distribution of M variables. So in each step of the Gibbs sampling, one of these variables is updated by drawing from its conditional distribution given the other variables. Let's have a closer look. So we initialize these M variables to some value, and then for T iterations, tau, we have M substeps, so 1 to M substeps, where we say, well, now let's start with subvariable Z1. Let's create an update by sampling from C1, so we draw from that distribution. It's an actual draw from the distribution. Of C1 given all the other variables. Then we update C2 by drawing from the conditional distribution of C2 given all the other variables. And we have C1 is already updated, so we take that updated version of that variable. And so on until we made draws from all conditional distributions from all these variables in our model, and then we iterate. Repeat 1,000 times, 2,000 times, 3,000 times, and so on. Yeah? If we look at immediately subsequent time steps, tau plus 1, then these samples are quite correlated due to the Markov chain. So we got to time step tau plus 1 from the location of tau. So probably it will be a similar location, no? But if we iterate this couple of 100 times or so, no, then the overall distribution may move in a different direction. Yeah, and then after capital T time steps, and these can be very many, yeah, thousands of time steps, no? If we then say, let's now take the state of our variables as this sample, yeah, then this can have moved to some location in our probability space, no? That is very, very different from the starting position, no? The sample of the complex distribution is a single state after T iterations, no? So after M times T of these individual draws. Okay. So, what does this mean for Bayesian-Gaussian mixture model fitting? We have these parameters, pi, the means, so the weights for the mixtures, the means of the Gaussians, and the covariances of these components. Yeah? And we want these to become variables in a Bayesian model, yeah? Because the idea is to make also the number of components part of the inference process. You know? So if they all shall be arranged in a Bayesian model, then they require prior distributions. No? So okay, priors as a general remark, this is just a little footnote here, and you probably know this from your bachelor's. When there are few observations, then the prior dominates the posterior, and when more observations become available, then the influence of the prior diminishes and the likelihood takes over. Okay. But anyways, so we want this all in a Bayesian model. So these variables require prior distributions. Now, if we think about Bayes' formula, I mean, posterior equals likelihood times prior, then the question is what prior to choose? And the answer is it should be a so-called conjugate prior. Yeah, because this is really what makes the math doable. What is a conjugate prior? A conjugate prior is a function that is chosen in such a way that the likelihood distribution, so the likelihood function or whatever, multiplied with the conjugate prior gives a functional or has a functional form for the posterior distribution that has the same form as the prior. So in that sense, you can say, okay, I'm starting here with a prior, let's say, from the exponential distribution, and if I multiply it with that likelihood, because this exponential distribution there is a conjugate to the likelihood, the result will again be from an exponential distribution. And this is very useful, because then we can say, well, perfect, we can reuse the result and gradually, for example, add more data. So we can use it as a prior again, then for including more data. This is kind of like a repetition of the experiment, you could say, no? Or I have more observations now. Or you could say, well, okay, now if this is part of a bigger framework, bigger expression somehow, I can compose it. I can compose this posterior, and I know already the functional form of that posterior will also be, for example, an exponential function or so. So I know what to expect, and maybe I can use this then as a prior elsewhere. Okay. When we are seeking to define such a conjugate prior, then usually we also require parameters for those. And now if we say, okay, pi, mu k, and the covariance sigma k shall become variables, then there are these like hyperpriors, the parameters to the priors. Then these are usually set to fixed quantities, no? In order not to infinitely iterate. Okay, so let's have a look again at this picture. I already showed it to you in the previous lecture. It's from Wikipedia. It's a graphical model for Bayesian GMM fitting. And let's study this again. So we have the actual data here, the observations that we make, and this is what we want to fit our Gaussian mixture model to. Now there are these components here from which the data presumably has been generated, and we have the Zi as the hidden variables from which, like, we're interested in the responsibilities then. And let's now look at the variables that constitute the actual model. So we have, we have here a distribution for the components themselves. So a certain probability mass function that component 1 is selected, component 2, component 3. So this is a discrete distribution for the k components. And this has a prior distribution. It will be a Dirichlet distribution. I'm coming to this in a second. Parameterized with a hyperprior beta. And then these k components, they have means mu k, and they have covariances, or here written as standard deviations, but never mind, sigma k squared, where the mean depends on the covariance. So there's a dependency here, and both of these, they also have hyperpriors. So the mean depends on a mu 0 and a lambda, and the covariance depends on a nu and some sigma 0 that needs to be defined. Yeah? And what we will see is, well, we can choose as a hyperprior for mu, we can choose a Gaussian. So the mu 0 is like a general mean from which all these Gaussian means are drawn. And the lambda is like usually you choose it very widely, no? Or like is the precision for, so the inverse of the standard deviation of a Gaussian from which all the means of all the components are drawn. And for the covariance matrix, we can use a so-called Wishart distribution, that is the conjugate prior for the covariance here, that also has these two hyperparameters. I forgot which ones. Okay, so let's write this down really quickly. So the discrete mixture weights pi require a prior. We talked about this. The conjugate prior for a discrete distribution is the so-called Dirichlet distribution. We haven't formally introduced them. I'm just dropping the name such that you know. So the Dirichlet distribution for a discrete distribution pi depends on m hyperparameters for m components. But they are oftentimes chosen as one fixed value alpha 0. So same prior probability for each of these components. And then we need for the mean mu k and the covariance sigma k, we also require priors. So what we saw from the graphical model, mean and covariance can be decomposed as the mean depends on the covariance and the covariance stands on its own, and the conjugate prior for this is a so-called Gauss-Wishart distribution, where the Gauss is actually part of the mean here. The variables here, I use Bishop's notation, not Wikipedia's, so this is why we have an M0 and beta 0. And the Wishart distribution here, in Bishop's notation again, has these priors nu and v. No? Okay, but maybe we can look a bit into the details in our meeting, but we don't need to emphasize on them here. Okay, and then with all these variables, their priors defined and so on, we can apply the Gibbs sampling to these Gaussian mixture models. So what you actually need to do is to iteratively sample from each of these distributions conditioned on the other variables. No? And we will look at Rasmussen's paper in our joint meeting to understand this a bit better. You can also look at it in advance now. I think it's quite instructive. The responsibilities are sampled for k components plus 1. And the plus 1 is a very smart move. So if the k plus 1th component is selected, then we are gaining one component. And if at the end of an iteration one component less is selected, so k minus 1 components in total, then we're shrinking the model, so we lose one component. Yeah? So this is the way how it can dynamically grow and shrink the magnitude. And this is just what you like. The skip sampler, it just iteratively repeats until the number of components somewhat stabilizes within some interval. It never really stabilizes, because in every iteration you could create new components or abandon existing components. But in practice, you can just say, yeah, okay, now it seems as if it's oscillating around these and these values, so now I stop. No? Okay. And when you stop, so when stopping the iteration, when stopping the iteration, then the current state, so the current parameterization is one sample from that Markov chain Monte Carlo method. Yeah? So it's one specific Gaussian mixture model from the universe of the valid Gaussian mixture models with a specific number of components and parameters. Yeah? Let's have a look at one of the result figures in Rasmussen's paper. It consists of two parts. On the left-hand side, we see a plot. Here's the so-called iteration lag time. It's the time between two iterations. And on the y-axis, there is the autocovariance coefficient shown. It's not formally defined here, but what does it mean? So it means if let me annotate this, hold on. If I'm checking, for example, at iteration 100 or so, or if I'm at iteration tau and I'm checking the same parameters at iteration tau plus 100 again, then they are correlated to a certain degree. This is this autocovariance coefficient that is shown there. Yeah? They are correlated to a certain degree, and the further away these iterations are, the lower this autocorrelation gets. So this autocorrelation, it goes down, goes down, goes down. The authors say, if you check the caption here, that after approximately 270 iteration, they are leaving this range of an effective correlation between. So the effective correlation length is approximately 270 iterations. Yeah. But you see, like, depending on where you set your correlation threshold, you might go as far as 800 or so iterations apart to really be in a different part of this GMM space. Yeah? If we check the right-hand side of the figure, this is also interesting. Here we have the iteration numbers in absolute. They are fitting something like a 20 or 30 component model, like to a spiral of data. I haven't shown it here. No? And on the y-axis here, there's they show the number of represented components in their Gaussian mixture model. No? Okay. And it turns out we have here, like in the first, let's say 800 or 1000 iterations, we have a startup phase where the number of components in the solution slowly increases until it reaches here something like 15 to 20 components. And then it kind of, like in the further progress, it kind of oscillates here at around these numbers. Yeah. And you can think about this like as a walk through the space of possible Gaussian mixture models with different parameters. Yeah. And it walks there through this MCMC iteration, 2000, 3000, 4000, walks. And at some point, one would say, yeah, it's okay, I'm aborting this whole process and pick like whatever solution I have at a specific location. There's still a considerable variance if you look at this somewhat coarse plot, no? So could be that you get a 20 component solution, could also be that you get a 15 component solution there, but this is the statistical nature also of this walk through the GMM field. But in any case, you can say, okay, now I'm essentially beyond this initial startup phase. So any of these solutions certainly has some justification or so with respect to our model. Okay, so yeah, I think that's an interesting way to think about model fitting and optimization to gradually approach the parameters to the data at hand, but it's a fully sampling based solution, so it's not a maximum likelihood solution or so in any way. And the fit is essentially a result of combining these priors with the likelihoods for these parameters in every sub-iteration of the process. No? Okay. Good. So we can have a closer look at this in our meeting. Maybe one closing remark. I already mentioned, the notion of one sample, it depends a bit on the scale at which you look at a model. But if we now talk from the perspective of these algorithms, then one sample from the perspective of inversion sampling requires one draw, like one physical draw. Analytic sampling also requires one draw. Rejection sampling and adaptive rejection sampling always require two draws. So one's for the Z0, one for the PZ. And then it multiplies with the number of rejects. And the number of rejects depends on how much slack there is between the actual distribution P and the envelope Q. Markov chain Monte Carlo sampling has many subdraws. So M for the number of variables and T for the number of time steps that we want to walk. So M times T subdraws. Okay. Let's talk more about further details and everything on Monday. The paper by Rasmussen is online if you want to have a look. It's quite mathy, but it's also instructive. If you want to have a look, please check it out. And I'm looking forward to meeting you then. Yeah. Bye-bye.